All right, let's talk about something that secretly organizes your whole life, from your Spotify playlists to how companies handle massive amounts of data. It's called set theory. Now, I know it sounds super academic, right? But trust me, you're already using the main ideas every single day. We're going to break down how this amazing tool helps us find a little bit of order in all the chaos. I mean, think about it for a second. We are just bombarded with information, with objects, with ideas all the time. How do our brains even begin to sort through it all, find the connections, and make any sense of it? Well, that fundamental question, that's exactly what set theory was designed to tackle. Okay, let's make this super simple. Imagine you're looking at a desk. You've got some journals, some magazines, and a laptop. Right away, your brain probably groups the journals and magazines together as stuff to read, and the laptop is, well, it's something else entirely. That little automatic act of grouping things, that's it. That's the heart of set theory, right there in action. So, here's our game plan for today. First, we'll nail down what a set actually is. Then, we'll learn the lingo, how to talk about them. We'll look at the different kinds of sets you'll run into, see how they play together, and then the big one. We'll see why any of this actually matters in the real world. Okay, let's dive right in. What in the world is a set? At its core, it's just a simple, powerful idea about creating order out of messy collections of things.
So here's the official definition. A set is just a collection of distinct, well-defined objects. Now, well-defined is the really important part here. It just means we can tell for sure if something belongs or not. For example, the set of all magazines on the table is totally clear. But if I said the set of all interesting magazines, well, what's interesting to me might be boring to you, so that's not well-defined. And each thing inside a set, we just call that an element. Simple as that. Just like any specialized field, math has its own kind of shorthand, its own grammar. So let's check out the two main ways we can actually write down a set.
Okay, so on the left, you've got the roster method. This is the easy one. You literally just make a list of everything in the set. Super straightforward. But what if your set has like a million things in it? That's where the set builder method on the right becomes a lifesaver. Instead of listing everything out, you just write a rule. So here, W is the set of all numbers, we'll call them T, that follow a specific rule. T has to be an even number between 81 and 100. It's a much more elegant and compact way to describe really big sets. All right, it turns out not all sets are created equal. They come in a few different flavors, so let's meet the family and get to know the main types you're going to see over and over again. First up, we have the null set, or the empty set. It's a set with, you guessed it, absolutely nothing inside. Think the set of all chickens with lips. Next, the singleton set, which is just a set with one and only one element. Then you've got a finite set, which just means you could, in theory, count everything in it even if it's a huge number. And finally, the universal set. This one's important. It's like the universe for the problem you're working on. It's the big master set that contains everything you're currently talking about.
Okay, this is where it gets really useful, seeing how sets relate to each other. If every single element of set B is also inside of set A, we say B is a subset of A. Think of it like this. The set of corgis is a subset of the set of all dogs. Makes sense, right? But for it to be a proper subset, set A needs to have everything B has, plus at least one extra thing. So corgis is a proper subset of all dogs because the dog set also has poodles and terriers and so on. A proper subset is always smaller than the set it's in. Here's another one that can trip people up, but it's pretty simple. Equal sets mean they have the exact same stuff inside them. The order doesn't matter, but the elements have to be identical. Equivalent sets are a little different. They just have to have the same number of elements. So the set apple, banana, cherry is equivalent to the set 1, 2, 3 because they both have 3 things in them, but they are definitely not equal. See the difference? All right, so now we know the different kinds of sets, but what can we actually do with them? Well, this is where we get into the really cool stuff, the basic operations that let us combine and compare them. First up is the union. You can think of this like a merger. You take two sets, A and B, and you smush them together to create one big new set that has every unique element from both. The one big rule here is no repeats. If an element is in both sets, it only appears once in the final union. And this example shows it perfectly. Set Q has 1, 2, 3, and 5. Set W has 3, 4, 5, and 7. When you make their union, you just combine them all. But look closely.
See how 3 and 5 were in both of the original sets? They only show up one time in the final result. No duplicates. That's the key.
All right, next we have the intersection. Now, if union is all about combining everything, intersection is the complete opposite. It's about finding what they share. The intersection of A and B is a new set that contains only the elements that are in both A and B. It's the common ground, the overlap.
So let's look at this example. Set A has 2, 3, and 4. Set B has 3, 4, and 6. So what's in both of them? Just the numbers 3 and 4. And there you have it. The intersection is the set 3, 4. It's basically a way of filtering out everything except what two sets have in common. And our last big operation for today is the difference. When you see A minus B, what we're really asking is, what's left in set A after we take away anything it shares with set B? It's pretty much just like subtraction, but for sets.
Okay, check this out. We're doing set Y minus set T. So we start with all the letters in Y. Then we look over at set T and we remove any letters that are also in Y. In this case, that's W, R, and Y. So what are we left with from our original set Y? Just U, P, and O. And that's our answer.
So, we've learned the terms, we've learned the operations, but you might be thinking, okay, cool, but why does any of this actually matter? Well, it matters because this gives us an incredible way to visualize relationships and, believe it or not, solve some really complex problems. And the most famous tool for doing this is, of course, the Venn diagram. I am sure you've seen these a million times. Each circle represents a set. The total space covered by both circles, that's their union. And that really important overlapping part in the middle, yep, that's their intersection. It's such a simple but brilliant way to see how sets are connected. Okay, time to put all this theory to the test with a real problem. Imagine a big survey of 1,000 families. We ask them what kind of fuel they use for cooking. We get all this data back. We know how many use electricity, how many use gas, and how many use kerosene. But the million-dollar question is, how do we figure out how many families use all three? And here's the data we have. We know the totals for each fuel type, and we know the overlaps between any two of them. But that key number, the people who use all three, is hidden somewhere inside all of this. I mean, trying to figure this out just by staring at the numbers would be a total nightmare. But this is exactly the kind of mess that set theory was built to clean up. And there it is. The answer is 48. By using a really powerful formula from set theory, we can systematically take our data, add up the big groups, then subtract the parts where we double counted, and it allows us to perfectly isolate that one piece of information we were missing. Set theory just cuts right through all that complexity and gives us one single clear number. Pretty amazing, right? So think about it. We just went from sorting stuff on a desk all the way to solving a tricky data puzzle. What we've seen is that set theory isn't just some abstract math concept. It's a basic language for describing groups and how they relate. So the real question I want to leave you with is this. Now that you have this new way of seeing structure everywhere, what kind of hidden patterns are you going to start noticing in the world around you?